Hello, everybody. Welcome to our RAG Hack live streams.
RAG Hack is a free global hackathon happening from September 3rd to 16th. RAG is a technique to get a large language model to answer questions based off your data. We have more than 25 live streams teaching you how to build RAG apps with different Microsoft technologies, plus 10 cash prizes for the best RAG apps in each category. So we're super excited to have you join us for this RAG Hack. And now a word from our friends at Reactor.
Hello, everyone, and thank you for joining us for today's session. My name is Askia, and I am the event coordinator for the Redmond Reactor. Before we get started, we've got a few things to go over. So if you could please take a moment to look at our code of conduct. We seek to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional, and stay on topic. We're going to share useful links throughout the chat. And this session is going to be recorded and will be available on demand in 24 to 48 hours on the Microsoft Reactor YouTube channel. That brings us to today's session. We've got Pamela and Farzad, and session today is going to run approximately for 1 hour with time for questions throughout. And so I will now turn it over to our speaker.
Hello, everyone. I'm Pamela. I'll be speaking later in the session, and Farzad will be starting us off.
Awesome. All righty. Hey, everyone. I'm Farzad Sunavala. I am part of the Azure AI Search product group. I'm a product manager over there, and I'm excited to be talking about RAG with Azure AI Search today, along with my rockstar colleague, Pamela. She's going to be chiming in as well. All righty. So let's go ahead and get started with the agenda. So we're going to start off today with just kind of an overall introduction to RAG, or Retrieval Augmented Generation. We're going to go through an overview of kind of what are vectors and vector embeddings, and of course, vector search. Then we're going to talk about the state-of-the-art retrieval capabilities within Azure AI Search. We'll also talk about how to set up the optimal data ingestion pipeline. And finally, we'll walk through how to evaluate answer quality and then productize your application to go ahead and get started. With that, let's get started and talk about RAG. So what is RAG? Let's talk about Retrieval Augmented Generation. So before kind of going into what RAG is as a kind of pattern and architecture, let's start about kind of what the pain point is. So LLMs, or large language models, are basically next word predictors. And so they're really good at writing text fluently in many different languages, but they're not necessarily guaranteed to produce text that is relevant or accurate. And in the slide, you could kind of see a couple of examples. So in this case, we might ask an LLM, something like GPT-4o, to write code for a Python package. And so it'll write code according to what it's seen in its most training data. All models have a pre-trained data corpus, usually up to a certain cutoff date, something like, I don't know, January 2024. And in some cases, it doesn't reflect the most current documentation. And so the example screenshot over here, it produced outdated code based on an older version of the package. And so that is an example of public knowledge, and it can potentially be resolved by updating to a newer version of the model. So kind of with most enterprise and kind of more important use cases, private knowledge is what you really want to search over, right? So LLMs, they don't inherently have access to this private or internal knowledge. So things like company documents, different knowledge bases, things that are within your own kind of private ecosystem. And so it'll answer based off what they saw in their training data most of the time, unless you have some sort of mechanism to give this private data. And then so that's kind of why we need to find a better way to bring internal knowledge and updated public knowledge into your retrieval augmented generation or interaction with large language models using a pattern known as retrieval augmented generation. So how do you kind of incorporate this domain knowledge? So in this slide, you could kind of talk about two main ways. So one is kind of just, it's actually for some reason not showing on the slide, but one's prompt engineering. And prompt engineering is all about just being very, very specific. Tell it a version that usually large language models have prompt engineering best practices. And this is all like saying things like you are an AI assistant that's going to help me with Python programming. And so you can get very, very granular in terms of the system prompt that you give one of these large language models. And that's usually a good starting point. But this only works if the answer is somewhere within that pre-trained model. So something to consider. Then there's a concept of fine-tuning. So fine-tuning is really just starting with the base model. So something like you could use Llama 3, you can use GPT-4, whatever it might be. And fine-tuning is how you teach a language model new skills. And a good way to kind of think about it is permanently adjusting kind of the model, okay? And so a good way to fine-tune is start with the base model and add something like 200 examples and then run the training again. And so fine-tuning, some things to note, it could actually be expensive, kind of both computationally and fiscally in some cases. And so in some cases, it may not be the best mechanism to incorporate domain knowledge. But then there's this concept of retrieval augmentation. So this is all about teaching your language model new facts. Okay, so how can you retrieve from your private or internal knowledge base and then add or augment your language model with the retrieved data you get from your internal knowledge? And so you're augmenting that prompt or question to with your grounded data to the large language model. Okay, so that brings us to retrieval augmented generation. So I'm just going to put up all the different artifacts on this slide over here. Whoops. And in this example, you could kind of see that this demo, there's a user question. Someone asks, do my company perks cover underwater activities? And what happens is this question goes to some sort of internal knowledge base. We'll talk about vector databases and vector representations in a bit, but then you search this internal knowledge base. And this could contain things in this example use case, things like HR documents, okay? And so this RAG flow is essentially, you have a user question, you go retrieve your most relevant documents, just like conventional information retrieval, and then ground your large language model. And so you're giving that GPT-4o, whatever Phi-3, whatever large language model or language model you're using to get a well-grounded response. And this is where quality in the context of generative AI applications is really, really important. Okay, so moving on, let's talk about components of high-quality RAG. Okay, so when you build a RAG application, there are kind of three main ingredients that really contribute to the overall kind of generative AI quality. And when it comes to business value, the quality that you get out of these language models is really the most value add thing, right? So we need powerful search capabilities to be able to search massive corpuses of data. Okay, so for optimal results, you can use things like hybrid search, which we'll talk about a little bit later and actually show some demos, which is a combination of vector search and full text search. Okay, and then also we'll also show about semantic re-ranking, which is an advanced capability to make sure that you're always getting the best results from your retrieval system, and why getting them at the top is really, really important in the context of RAG. Okay, you also need a well-prepared data to insert into your vector database or retrieval system or search index, okay? So these document chunks, we'll talk about chunking strategies in a bit as well, should be a reasonable size, okay? Not too small, not too big. And the reason why you have to chunk is because when you create vector embeddings, another pretty important component when it comes to building a RAG application or RAG pipeline, is that each of these vector embedding models has a certain input, and that's just based upon the design of a lot of these embedding models. So chunking is a very important strategy, not just to meet the requirements of creating vector embeddings, but also in terms of assessing the actual quality of the actual chunks or documents that you actually contain inside of your retrieval system. Okay, and then of course, kind of the number one here, the bullet point, just a sophisticated LLM. Large language models are moving so rapidly. I feel like there's a new one coming at least like once a month with upgraded versions. So using a very sophisticated large language model to essentially adhere to your system prompt, whatever you're telling it to do, to stay on topic. Of course, Ideally support for something like function calling, which is quite an advanced capability of language models, where you could essentially ask it certain things to respond in a certain format. It's overall where you're going to have a majority of the opportunity, or majority of the business value will come from this large language model, but you want to make sure you're feeding it the right ingredients when it comes to retrieval augmented generation. Okay, so we're going to dive into each of these components, and we'll share everything we've learned on how to build a high quality RAG application. Okay, and why Azure AI Search should be your choice. All right, so let's talk about Vectors 101. Okay, so let's take a step back, and I mentioned vector embeddings and kind of the importance of why you even need it inside of your search applications. But let's first talk about what is a vector embedding. So essentially a vector is kind of just a universal representation of data. Okay, so a vector embedding is a list of numbers, kind of like what you see here, that represents a particular input of, in this case, text, but it can be anything, can be most modalities inside of a particular embedding space. Okay. And so there are a lot of different embedding models that take different inputs. Over here, you can see most of these take text, probably the most common ones for most use cases, but multimodal scenarios are really popular. We'll talk about that in a bit. But you can see sentence transformers, SBERT, OpenAI, text embedding models, very, very popular, very powerful vector embedding models, where if anyone is a data science, like 10 years ago, training and hosting and your PyTorch kind of embedding model, it was a big pain. But now there's these embedding models that are kind of derived from some of these language model companies that are really, really state of the art, where all you do is give it input text or whatever modality, and bam, you get an output immediately just by doing a REST API call, and you get a pretty good representation of what your data looks like. And there's a lot of different things you could do once you have that vector embedding. Okay. So now that I kind of talked about the different kinds of embedding models, I'm actually going to quickly show an example of kind of what this looks like. Okay, so I'm just going to move to a GitHub here, and you could actually find all the different notebooks and the Python samples that are being shown in this call today within this Azure sample GitHub repo, RAG with Azure AI Search notebooks. Okay, and so I'm going to go to this vector embeddings. I think actually you have it open over here. Awesome. So what I'm going to go ahead and quickly walk you through, just very, very briefly at a high level, how to actually get started generating these embeddings. Okay, so in this example, we're going to use Azure OpenAI embeddings, which are essentially the same as OpenAI's. So I'm just going to define some environment variables over here. You can get your Azure OpenAI service API or service endpoint and API key, or in this case, we're going to use managed identity to authenticate to the service and define these variables over here. So in this vector representation example, I'm actually going to zoom in just a bit. You can see that I have a sentence. A dog just walked past my house and yipped like a Martian. Okay, so what if I want to turn this sentence into a vector embedding? I talked about all the different models, how easy it is, and literally within 2 lines of code, you can see your vector embedding of this sentence. So I'm just creating a response. I imported the OpenAI client, and I'm just calling the embeddings.create method, which takes an arguments of my model, which I get from my Azure OpenAI service, and of course, the input sentence that I defined earlier in this variable. And then bam, I get I believe, 1536 dimension very long embedding. And what this does is this is that vector representation of that input sentence, right? So really, really, really powerful, super, super easy to do. Okay, so I'm gonna go back to my slides over here. Let me go ahead and go to the next slide. So now that we have these vector embeddings, something we can do is compute vector similarity. Okay, so this is really, really important because there's multiple different distance metrics that we can use, but probably the most common one that a lot of embedding models use today is cosine similarity. And usually a lot of people ask, what similarity metric do I use for my vector embeddings if I want to do things like semantic search, which we'll talk about in a bit. Usually what I say is look at whatever the guidance is from the embedding model, whatever distance metric the model was trained on. That's what you want to use. In our case, you can actually go to the OpenAI embedding documentation. You could actually see that they recommend using cosine similarity. So in this case, we're going to show a simple cosine similarity function for those similar to Python, I believe using NumPy, or you can go on Wikipedia and find the cosine similarity function yourself. Yeah, let's see what we could do with, now that we have vector embeddings, and calculate our cosine similarity. Okay, so I'm going to go back to my GitHub over here. And you can see here that in this code, I'm actually using NumPy, pandas, and I have my cosine similarity function that I've defined. Okay, so I'm not going to focus too much on the function, but I'm just going to show kind of how this works. So I have 3 sentences in this right here. New movie is awesome, new movie is awesome, new movie is awesome. And then I have 2 sentences, in my sentence 2 array, I have the new movie is awesome, the recent movie is so good, and a bunch of gibberish, okay? So what I want to do is I want to find the cosine distance between the different sentences inside of each of these arrays. So what essentially I'm doing here is I'm going to create embeddings for all these different input sentences, and then essentially pass those into my cosine similarity as the A and B arguments, and then essentially just return what the cosine similarity is actually going to return. Okay, so if you can see over here, I have the sentence 1, kind of my first column over here, the sentences 2 in my second column, and you can see the different scores. Okay, so these are my cosine similarity scores. Okay, my cosine distances. So you can see here, the new movie is awesome, the new movie is awesome. These input characters, these input tokens, to be specific, they're identical. Okay, so if the OpenAI embedding model function worked correctly, it should actually return to overlapping identical embedding vectors like I showed earlier over here. And once you do the cosine similarity function, you can actually see that that gives a perfect overlapping match inside of the high dimensional vector space. Okay, so that's why I get a score of 1. Right, and then the same thing for this recent movie is so good. It's kind of very semantically similar to new movie is awesome. So that's why I get a cosine distance of 0.9191. Okay, so very, very similar. And then, of course, I have a bunch of gibberish that I put into this embedding model, which is why I get not the best cosine similarity score in this case. And so this is really, really powerful when it comes to, you could kind of use this as the building blocks for kind of building semantic search applications, then building full out vector databases or retrieval systems that are kind of the foundation for building a very, very high quality RAG application. Okay, so with that, I'm going to go back to my PowerPoint. Okay, and now we can talk about vector search. So essentially, all vector search is given a search query, we compute an embedding, then we find something called the k-closest vectors. Okay, and there's kind of 2 main ways to kind of do vector search. One is kind of to search exhaustively. A technique commonly known as exhaustive KNN, and I think we'll talk about that in a bit. And then search using approximations or approximate nearest neighbor. We'll talk about nearest neighbors as well. So here's kind of just the end user flow, I guess, to some extent. And I'll show you a quick example over here. So in this query, we have tortoise. You can create an OpenAI embedding. You get something like a very large array of numbers. You can search through those existing vectors, whatever you vectorize inside of your document corpus. And so you have your query vector and you have your document vector, and then you have whatever algorithm, in this case, your k nearest neighbors, to search through all those. And then you get your documents in order along with your, in this case, cosine similarity score. All right. So I'm going to go back to my GitHub notebook. And you can see over here, now what I'm going to do is actually do a vector search, right? So I'm going to load these OpenAI movies.json available in this GitHub as well. And it has a bunch of different movies. And in this case, I'm just going to compute the query vector for 101 Dalmatians, okay? And so what it's doing over here, now I'm actually calling that same function that I defined earlier, that create embeddings function, passing in the same arguments. I'm going to return that vector for this query. And so what I'm also now going to do is compute the cosine similarity for between each query and each movie title. Okay, so I'm going to use that same cosine similarity function that I did earlier, and then I'm just going to display the results in a pandas data frame in terms of the columns movie and score. Okay, so show me the most similar results to 101 Dalmatians inside of my movie data set. And that's what you can see here. We have of course, our IDs, our movies, and our scores. And as anticipated, 101 Dalmatians is going to be that really good match. Then 102 Dalmatians, and then so on. You can see some movies that I guess have animals in them to some extent, and it's ranking based upon that semantic similarity. Okay, so really powerful vector search capabilities over there. All right. So now let's talk about Azure AI Search. Okay, so now we're really going to deep dive into how these fundamental concepts of vectors and vector search and how you can kind of use them kind of in a real production, high quality retrieval system application. So what is kind of Azure AI Search? Azure AI Search is a comprehensive search solution that includes features specifically built with RAG in mind. Okay, Azure AI Search is also integrated with popular open source integrations like LangChain, Llama Index, Azure OpenAI Service, Azure AI Studio, Semantic Kernel, and a whole bunch more. Okay, so basically, whenever you're building your RAG applications, you can use Azure AI Search as your retriever inside of that RAG architecture. Okay, and so there's lots of different ways to get started. AI search, we actually introduced vector search, I believe, almost a year ago, a little over a year ago in preview, and now it's generally available as of Ignite 2023. And we have many customers around the globe using it for various different applications. And so what we're going to do now is we're actually going to go through an example of how to get started with Azure AI Search. All right. So what I'm going to do is I'm going to go back to my GitHub notebook. Again, you can find this inside of the GitHub repository. And we're going to do an Azure AI Search vector search step by step. Okay. So this is going to kind of go through just creating a search index. Then we'll talk about the vector search strategies in a bit. So how to get started. So I'm going to import these libraries over here. So we have Azure Identity for authentication, environment variables, and then I'm actually using, you can do pip install Azure Search documents on PyPy to get the Azure Search Python documents, Azure AI Search SDK in Python. And you can get your service information inside the Azure portal and your AI Search service, or call our management API to get the relevant information here. So you have your service, your endpoint, and then we recommend using managed identity to authenticate. And so now what I want to do is I want to create a teeny tiny index. Okay, so I'm going to import certain classes. You can see here, we'll talk about HNSW in a bit. Different search fields, vector search, the vector algorithm that I want to use, and vector profile. Okay, so in order to create this teeny tiny index, I'm going to have probably the simplest schema you'll ever make. So I have ID and embedding. Okay, so what I'm going to do here is I have simple field ID. So this is this is my key field essentially inside of my index. And then I'm going to have an embedding field. Okay, so this embedding field is where I'm going to put my vector embeddings. Okay, so I'm going to have type search collection data type dot single. So that's my OData syntax for the primitive type that I want to use for this vector. Searchable equals true. In this case, we're going to do a very simple example. So we're going to do vector search dimensions equals 3. And then I have my embedding profile over here, which I then create over here. Okay, so inside of this vector search class, we have algorithms. And inside of algorithms, you can create two different types of algorithms. One, HNSW, and one is exhaustive KNN. So that's the difference between searching exhaustively versus a approximate approach using HNSW. In this case, we're going to use HNSW. So we have our HNSW config over here and cosine similarity as our metric, okay? And there's a whole bunch of different parameters you can configure as well if you want to deep dive more into how the HNSW algorithm works, okay? So now I simply call the create index function on index client, and I have my first vector search index ready to go, okay? So next I'm going to go ahead and insert a few documents. So all this looks like is calling the search client, okay, over here, pass in the same arguments over here, endpoint, the index name, and my credential, how I'm authenticating. And I'm just going to use a concept called the push API, which in this case, you can call the function upload documents in Python and pass in an array of the documents or nodes that you want to insert into your vector search index. And so because my schema is super, super lightweight, just to keep things simple, I have ID and embedding, okay? And this is just a demo scenario. And so if I want to search using vector similarity, here's exactly how it would work. Okay, so instead of defining that NumPy cosine similarity function and the dot product and all that jazz, all I have to do here is, in this case, pass in to do a pure vector search, the vectorized query class. Inside of the vectorized query class, I pass in the vector. In this case, I'm just putting in random numbers, saying k nearest neighbors equals 3. So this is saying, hey, I only want to return 3 of the nearest neighbors inside of my vector space. So I should get 3 results inside of my console. And then the field that I want to target is my embedding field. In this case, we have 1 embedding field, so we're going to just put the embedding field here. But we could also put more, and we'll talk about that soon. Then I'm just going to print out the results. So you can see here, it's doing a approximate nearest neighbor vector search using HNSW. And if you want, you could double check and fact check the math, and I get ID2 score of 0.36 for these different query vector from my document vectors. Okay, so that's essentially how pure vector search works. So I'm going to go back to my PowerPoint, okay, and quickly talk about these different vector search strategies, okay? So I talked about ANN search and exhaustive search. We'll just very, very briefly go into the actual capabilities. So there's ANN search, which is an approximate way of searching over your vector embeddings, okay? The big pros about ANN search, or approximate nearest neighbor search, it's a very fast, it's a very performance optimized vector indexing algorithm. Okay, so if you have applications where you kind of want to focus a lot on performance, so getting the fastest results, especially in production scenarios where you have very, very large vector indexes, like hundreds of thousands of documents or vectors, I would strongly consider using HNSW or ANN search. Okay. And then additionally, we have exhaustive KNN search. And so this is another vector indexing algorithm that we have, otherwise known as KNN or K nearest neighbors. So this is per query. You can actually use this per query. So if you can want to use exhaustive search as a query time parameter, even if you already defined an HNSW schema, you could do that as well to exhaustively. This could be good for finding like ground truth values when you're doing testing and things like that. Or you could build this into the schema. If you know that finding the exact nearest neighbor match inside of your vector index is important, you can use it as a vector indexing algorithm. And when it comes to storage, there's actually no vector index overhead. So in this case, in the context of Azure AI Search, if you use exhaustive, you'll notice that there's no vector index inside of your search service or search index. Okay. So those are the kind of 2 different vector search strategies that you can use. I'm quickly going to talk about the vector search query capabilities. So these are really, really important, especially when it comes to kind of building more advanced RAG applications in terms of when you start refining and iterating. We'll talk about evaluation in a bit. Using filters inside of your RAG application, specifically your AI search index, is a very, very important tool that you could use for refining search quality or optimizing search quality by refining the results you get back based upon certain criteria. Okay, so in this case, I recommend checking out our link. We have a very, very comprehensive Lucene filter syntax. You could pretty much do anything you want when it comes to filtering. So you can scope down things like dates, ranges, categories, geographic distances. And then also another very important topic is kind of role-based access control. And in Azure AI Search, we actually use the filter predicate to kind of enable that. And so I believe there may actually be a dedicated session on that as well. But I highly recommend reading up on how you can use the filter predicate to do things like role-based access control to make sure users, when you build your RAG application, are only seeing the results that they're supposed to see and have adequate permissions on seeing. Okay. We also have pre and post filtering. So real quick, pre-filter is great for very selective filters. And there's no kind of recall disruption when you use pre-filter. And we actually recommend using pre-filters for the majority of scenarios. I believe that's the default as well. Then there's post-filter. So post-filter is better for low selectivity filters, but you want to be careful because sometimes you may actually get empty results because of the filter being a little bit too restrictive, okay? Then there's a concept of multi-vector scenarios. So this is what I was talking about when you run your vectorized query. Previously, you could only target one vector, but now for like things like multi-vector scenarios or multimodal scenarios, which we'll show in a bit, you could actually target two different vectors inside of your search, two or more different vectors inside of your search index. So if you decide that, hey, I want to create a vector representation for my titles of my documents and the body or description of my documents, you could do that as well. And we actually use reciprocal rank fusion, a concept that we'll talk about with hybrid search in a bit, to fuse those different results together. So now you have vector representations of two different things within your documents that you can use to help your retrieval quality. Okay, so now on that note, multimodal vectors. So when you have images, when you have text together and you want to search over them, how does that really work? Okay, so the cool thing about vector embeddings is a lot of times they enable multimodal scenarios, okay? Because at the end of the day, that vector embedding is just like a universal representation of data, right? So whether you have images, sounds, MP3 files, graphs, like knowledge graphs or something like that, or whatever type of medium you may have, there's certain multimodal embeddings that take certain inputs, okay, of different modalities. One example that we're actually going to show here is actually using Azure AI Vision embeddings, okay, from the Florence foundational model as part of the image retrieval API inside of Azure AI Vision. Okay, so let's take a look at that. Let's go back to our GitHub notebook and look at image search. Okay, so you already know how to set up an index, so I'm not going to go through that for time's sake. And now we're going to go ahead and create a search index for images. Okay, so we have ID, we have file name, we have embedding. Okay, so still a pretty lightweight index. One thing you will note is our vector search dimensions. In this case, since we're going to use a real world scenario, we're going to use the Azure AI Vision embeddings, which has a dimensionality of 1024. Okay, so if you go to the vector search profiles, stays the same. I create my index. And so now what we want to do is we want to configure our Azure AI Computer Vision multimodal embeddings API, okay? And so I'm going to do my authentication. I can grab my service info and my Vision URL from the Azure portal or Management Plane REST API. Here's my model parameters, my authentication, bearer token. And to actually get this image embedding, I'm just going to define this function that calls the Vision URL. Notice that because I'm going to vectorize images, I'm using, even though it's a multimodal model, I'm going to use the vectorized image endpoint. And also, we could also vectorize text. So for my text function, I'm going to use the vectorized text endpoint, okay? And that's going to be important when we start searching, okay? So to add these image vectors to the search index, I have a catalog inside of this directory. And again, you can see all this inside of the URL aka.ms/AI-tour/image search. You can get the product images, upload the embeddings after these have been called, the image embeddings. You can see I'm calling it over here. And then uploading the ID, the file name, and the image embedding. Okay, so now what I want to do is I want to query using an images. Okay, so in this case, I'm going to go ahead and show a query image. Okay, so in this case, this is a T-light sand side.jpg. So you can see it's a T-light, and you can see the colors, and I don't know, looks pretty cool. So this is an image that I want to query, that I want to use as my query. So show me in my image catalog, what are the most similar images to this? Okay, semantic search over images. Okay, so now what I want to do is I can see that I do my vectorized query over these images, okay? Same properties, query vector of this. I'm just passing in that image URL, or alternatively, you could even pass in the image binary, K nearest neighbors equals 3, just give me 3 results back. And then fields, I'm going to target that embedding field, okay, that I have in my search index. Okay, so here I get the JPEGs. Let's take a look at what those looks like. You can see here it's a very similar. It's actually the same object, but a different angle of that T light. And so on. And you can also look at some of the other ones if you want, but this is my first result. So pretty cool. Okay, I'm going to do one more. I'll show now a text embedding for Lion King. So notice that before I defined a get text embedding function as well. So this is that true multimodal experience where inside of my search index, I stored the image embeddings, but I want to call the get text embedding function, which has that difference of vectorized text at the end, right, that I showed earlier. So now I'm going to search Lion King, but inside of my vector index, I only have image embeddings. There's no text, okay? And so what do I get back? You can see for Lion King, I get Hakuna Matata. And so if you've seen Lion King, very popular reference over there, okay? So that shows the multimodal capabilities that you can use within Azure AI Search and other Azure AI services as well. Okay, let's go back to the PowerPoint. So another approach that I'll talk about is hybrid search, okay? So hybrid search is really important. And the reason why it's really important is because a lot of times when you query over things, sometimes doing a semantic or vector search alone, sometimes won't actually give you the best possible results, okay? And these are really important if you're searching over things like that need a keyword-based match. So you need something that's identical to what you're querying in your query vector or your query to match something inside of your corpus. Okay, so the common algorithm that's used for this is called keyword search or BM25 specifically. And so with hybrid search, for those of you who use Azure AI Search historically, Azure AI Search was really just known for full text search or keyword search. But now that we added vector search, in addition to our query capabilities and storage capabilities as well, you could actually leverage this concept of hybrid search to get the best of both worlds to power your RAG quality, okay? So you have your vector search results, you have your keyword search results. How hybrid search works is we essentially use that concept that I mentioned earlier called reciprocal rank fusion, or RRF, to fuse those results together, okay? So both algorithms, that cosine similarity on the vector side that you defined, and your keyword search, usually BM25, we fuse both of those recall sets together, and then you get the most relevant results. Okay, so let's look at a quick demo of how hybrid search works. And so I'm going to go over here inside of this Azure AI Search. You can find the link at AI-Tour/search relevance to access this notebook and follow along. So again, I'm not going to go through this, but I'm going to set up the clients here. In this case, you can actually see I'm going to use my Azure OpenAI service again. I'm going to instantiate the Azure Search and OpenAI client. I define my get embedding. In this case, I'm just going to use text. So as I showed earlier, vector search is not always optimal. So in this case, if I do a search query for $45, excuse me, inside of my vector index that I already configured, I know it contains information, about money, something that I have inside of my document corpus. And so you can see here, I get back some scores, but there's no matching text. So is it really giving me the best results? Okay, so how can you compare this search for a text query? So you can see here inside of my corpus, I did a text query instead of a vector query. And you can see here, I have some HTML markup over here with the table, and I have the value $45 here. So this is exactly what I was looking at. Okay, but my vector search alone couldn't retrieve that inside of my top three candidates. So how is hybrid search going to play a significant role? So with hybrid search, you can use RRF to combine vector and text results. So now I'm going to do the exact same thing. The only difference that you'll see over here is that I'm actually going to pass in a text property into my hybrid search over here, and you can see that with search query over here. So that's going to be that raw text of $45 that I defined up here. So I'm passing in that raw search text query. And then I'm also going to pass in my vectorized query, okay? And so I have some logic just to display this in my console, and you can see here that now this output is going to be my result set. And so you can see here in this first place, it found that desired chunk or document that I was looking for. So in hybrid search, you get a better recall set depending upon what type of thing you want to query for, okay? So with that, I'm going to quickly go back to the slide deck and we'll talk about one step further in your RAG quality. So let's talk about optimal relevance, okay? So how can you use hybrid search with this other feature that Azure AI Search has called the semantic ranker, okay? So semantic ranker is really, really, really cool. Okay, so I'm going to show a bit how it works. So you have your keyword results, you have your vector results. In this case, for the query, what underwater activities can I do in the Bahamas? You get reciprocal rank fusion, you fuse those results together, and then you have this concept of a re-ranking model, which is exactly what the semantic ranker is inside of Azure AI Search, which was actually built in partnership with the Microsoft Bing team. So now you can see that you have better ranking. You get better precision or the ordered list inside of your retrieved documents from your hybrid search algorithm. Okay, so that's really important in the context of RAG, and we'll show you why. But first, I'll quickly show an example of how easy it is to use semantic ranking. Okay, so in this case, I'm going to use the search query, learning about underwater activities. I'm going to say, hey, show me the top 5 results. And you can see here, I'm not going to read through all the results, but you can see here, it's not optimal ordering, okay? So how do I really get a way better order in terms of finding my ground truth data set, okay? So now if I do learning about underwater activities, you can see here inside of my first place results, some of the lessons covered under Perks Plus include skiing and snowboarding, snowboarding lessons, scuba diving lessons, surfing lessons, horseback riding, and so on. There's probably more chunks with that. And so that gives me a lot better precision compared to the previous response, okay? So highly recommend using hybrid with semantic ranking. I'll go quickly to the next slide, and you'll see here a lot of experiments that we did as a product group. I highly recommend checking out a blog post that we posted last year at aka.ms/ragrelevance. You'll see a great deep dive into what the Azure AI Search data science team did into actually running some benchmarks on each of these different retrieval modes that I just talked about. And so you can see here, we actually partnered with a lot of customers that wanted to experiment with the semantic ranker model to make sure we have real world value add inside of our retrieval quality. And you can see here just the difference in NDCG, or normalized discounted cumulative gain, which is a common information retrieval evaluation metrics. That hybrid plus semantic ranker, that little a very bright orange bar in this bar graph, the significance it has in terms of your overall ranking and relevance on customer data sets, on beer, a very common industry benchmark that you could even run yourselves, and Miracle, another data set that's actually multilingual. To the beauty about vectors and even the semantic ranker, it's multilingual. So it works for virtually any language. So highly recommend taking advantage of a hybrid with semantic ranking. I think it's really, really cool because no other vector database or retrieval system can say you get the benefit of keyword match, you get the benefit of kind of your cosine similarity vector search of something like OpenAI embeddings, and then you also get the power behind Microsoft Bing re-ranking on top of that hybrid search experience. So the power of keyword match, the power of something like OpenAI vectors, and the power of Microsoft Bing powering your RAG quality. I think it's a really, really powerful value proposition, and it's very, very easy to get started, as I showed earlier. Here's a quick summary of the different types of queries. I highly recommend, we're about to talk about evaluation really soon, but I highly recommend evaluating There's different query classifications or certain queries where hybrid semantic ranker may not be the best. Like in this case, you can see here for keyword queries, like very specific things like that $45, that's probably when you want to do a keyword-based search. So running your evaluations and adjusting your retrieval modes based upon whatever types of queries work best are what we recommend. Okay. So with that, you can go, I'll quickly show building a RAG flow in Python, how that works. So I showed setting up Azure AI Search, but how do you actually perform RAG on this? So once I have an Azure AI Search index, I want to start throwing this in some language models. How do I do that? Okay, so I'm going to go back to this GitHub notebook here, and I'm going to do this relatively quickly just for time's sake. So over here, I'm going to set up my API clients, nothing really different that I'm doing over here. I'm going to prepare a user question. In this case, what does a product manager do? I'm going to generate an embedding from this, and now I'm going to retrieve matching documents. So I could pass in my vectorized query over here, as well as I'm doing a hybrid search. So I'm passing in the raw question as well, saying, hey, give me the top 5 results from my hybrid search. Actually, hybrid with semantic search, I'm sorry, to make sure I'm getting the best possible results. All right, so now you can read through here. I get directly this first chunk. The manager of product management will collaborate with internal teams, engineering, sales, marketing, finance, external partners. And this pretty much sounds exactly like my job. I think this is a good answer. All right. So you could look through the other retrieve results as well. So now that I know that I have a pretty well-grounded retrieval system, I want to go ahead and now use Azure OpenAI and this OpenAI client and the Python SDK to create a prompt. As I mentioned earlier, that's going to be your system prompt or your system message here. You're an AI system that helps company employees answer questions about the handbook. And I'm very specific with my prompt. You should definitely spend a lot of time on optimizing that as well. User message, this is going to be whatever the front end is for someone interacting with a chatbot, for example. And over here is pretty much how I pass in my Azure AI Search retrieve documents to the OpenAI client. And that's exactly what's happening over here. So I pass in that question. And you can see here what a product manager does. And I have GPT-4 powering this experience. And that's RAG. So we barely added anything and you get a full stack RAG application. So very, very, very cool.
Farzad, I do have a question that we get to ask now. There's a lot of interest in semantic ranker and hybrid search, which is great. So Wei asked, does the semantic re-ranker adhere to data residency requirements?
Yes. So everything you store inside of Azure AI Search, you definitely want to be mindful about what your requirements are. But the data, if it's stored in a given region, the semantic ranker is the models are hosted in the same region as your Azure AI Search region. So, for example, if your data has to stay in I don't know, UK South, and you're using Azure AI Search in UK South, then you know that if you're using semantic ranker, and of course, if you're embedding model as well, your Azure OpenAI or whatever embedding model you're using, as long as it's in the same regions, it will abide by whatever data residency requirements you may have. That's correct.
Sweet.
Cool. All righty. I think, so if you want a really, really great demo to showcase kind of in a production form, everything we just showed, along with a pretty clean UI to use for RAG applications. Pamela and a whole bunch of other folks did a lot of great work building this RAG on documents demo. Highly, highly recommend. I think it's one of the most viral GitHub repositories I've ever seen in my career. You can visit it at aka.ms/ragchat. Lots of great things, lots of great tools using Azure OpenAI, Azure AI Search, App Service, and a whole lot more. So highly recommend giving that a look. All right. So I'm going to very quickly go through this section because I want to get to evaluation. Why do we need to split documents? Okay, so splitting documents is important because LLMs have a limited context window. Okay, it's definitely increasing over time. But the need to split documents is important because of that embedding model that I said earlier. They have an input token limit. Okay, and so sometimes when an LLM receives too much information, it can get easily distracted by irrelevant details. There's a really great archive or AI research paper that I highly recommend reading called Lost in the Middle that actually shows something similar to this diagram that you see here, which is the number of documents in the input context and the different levels of accuracy. And you can actually see here that just because you think a model has a very high context window, if you're maxing it out all the time, the model most of the time is only going to pay attention to what's towards the beginning and what's towards the end. Okay, hence if you have a ground truth document that is inside of the middle, it's actually going to affect your overall relevance, right? So that's the importance of the need to adequately chunk your documents to a very appropriate size. And then of course, ties in directly with the semantic ranker value proposition to make sure that you're getting the best possible results towards the top from your retrieval system. Okay, and so you can actually see here, along with that blog post, different recall values, a very popular evaluation metric where we did different retrieval configurations and the different recall at 50 or evaluating the top 50 results based upon different input token sizes or chunk sizes. Okay. Chunk boundary strategy, again, very important concept as well. So you don't want to break your chunks like in the middle of a sentence. You want to be smart about how to chunk. So a good, very easy strategy is to have some overlap window between your chunks. So doing something like 10, or in this case, 25% overlap window yielded better recall quality. And there's quite advanced methodologies on how to chunk, which we'll probably say for another time. But chunking is definitely really, really important about RAG quality. Okay. So I'll quickly talk about data ingestion. So this is really, really, really cool. This is essentially a reference architecture flow on how data ingestion you can get data into Azure AI Search. Where you have blob storage, you can use something like Azure Document Intelligence, of course, Python, or some other libraries like Llama Index or LangChain. They have great libraries that have optimal kind of chunking strategies that you could experiment and evaluate with. Something like Azure OpenAI to vectorize your chunks. And then, of course, like I showed earlier, storing those inside of Azure AI Search. And so a lot of that is kind of a lot of effort. But now in Azure AI Search, we have a feature called integrated vectorization, which is actually no longer in preview as of a couple of weeks ago. It's actually generally available. So you could actually use this capability in production, where literally in a few clicks inside the Azure portal, you can go from your raw documents to chunking, to vectorization, to store it inside of your index, to automatically doing vector search queries literally within seconds. So I highly recommend visiting this link at aka.ms/intvec to learn more on how to get started using integrated vectorization. And with that, I will pass it to Pamela.
Pamela, you're muted still.
Thank you. That's my fault for muting myself. All right, so I was having too much fun responding to all the great questions in the chat. So let's talk about evaluating our answer quality, right? This is really important before we actually put a RAG app out in production. We want to make sure that we're actually getting good answers back from the model. So, what we want to know for a RAG application is, are these answers clear and understandable? Are they correct relative to the knowledge base, right? Because asking a question for one knowledge base might get a different answer than asking that question for another knowledge. Like, what does a product manager do? That might vary based on company, right? And then, are they formatted in the desired manner? Like, are they, as short or as long as we want them to be? Are the citations in the correct format? Like, are they in square brackets, right? So here are like 3 different answers for 3 different, prompts here. And the only one that I actually like is this one down here, because it's the right length and it has that citation in the format that I want. So that is, my gold star. And that's what I consider to be a high quality answer. So there are many, many factors that affect the quality of RAG answers, and that's what can make it, difficult to figure out what's the optimal settings, right? Because we've seen there's so many different components of a RAG flow. So we've got the actual search engine with Azure AI Search, right? We've seen all the different search options with hybrid and re-ranker. There's, how we prepared our data, what chunk size we use, what kind of overlap we did, what kind of formatting we did, how many results we're getting back. So a lot of things that go into the data preparation and the search. And then with the LLM itself, it's, which LLM are we using? Is it GPT-3.5? Is it GPT-4? Is it GPT-4o? What does our system prompt look like? What temperature are we setting? That was a question in the chat. Like for RAG, I like to use 0.3. That's worked the best in my evaluations. But that's something that you have to evaluate and look for yourself. So many different things and knobs that we can tweak. So if we're going to tweak one of those knobs, how do we have confidence that we've made a good, a good decision to improve our overall quality? So we can evaluate our RAG flows at multiple steps, right? So we can evaluate the retrieval system itself. And, we could use a similar approach to what Farzad was showing earlier in that blog post, the RAG relevance blog post, where you can measure recall and precision and, make sure that you're getting, really good results just from the retrieval alone. We could also evaluate the language models on their own. So there's actually a leaderboard that's doing this for it, that kind of evaluates language models based on how well they do for particular tasks. So you can look at that to get an idea for the metrics. And then finally, we really want to evaluate the full RAG stack because that is what users are going to see, right? They're going to see an answer. We want those answers to be good. So I have a basic demo in, in that repo that we've been showing, right? So here I'm going to evaluate the RAG answer quality. So first I set up my search in OpenAI, just like we've been showing. And then I'm running that full RAG. This is the same thing that Farzad just showed. So I ran that to get a question and answer and sources. And so now I can evaluate the quality of that answer. And we can actually use LLMs to evaluate the answers from LLMs. And it sounds kind of crazy to use an LLM to evaluate, another LLM. But it actually, according to research, is actually a pretty good approach. So one way of evaluating is to actually, send all this stuff into an LLM and then say, hey, was this a good answer, right? And you want to use a really, really good LLM for this, right? So you want to use like GPT-4, the highest quality LLM that you can use when you're doing your evaluations. So here, I set up my evaluation and I'm using this Promptful evals package, which has built-in evaluators. I can also write my own evaluators if I want. But for this case, I'm just going to use the built-in evaluations for relevance and groundedness. So relevance will decide whether an answer is relevant to the question. And then groundedness will decide whether an answer is grounded in the sources. So I run that and I see that they both get scores of 5, which is the highest score. So we want, generally want to see scores of 4 or 5. So that's how we could do an evaluation. Now, when I actually do evaluations, I've got this other repo, AI RAG Chat Evaluator, where I've set it up so that I've got like just a lot of command line tools that I can use in order to, run lots of evaluations in bulk, right? So I'll show you, I've got a RAG that's just on my own blog, and I often run evaluations on that because I can reason about the results pretty well since it's on my own blog and I know myself. So here I can go and, look at the results from all those evaluation runs. It's now being a little slow here. But let me also show, here we go. There we go. Okay. So we can see here, these are a bunch of evaluation runs that I did, right? And people were asking stuff about like temperature, right? So you can see I looked at temperature. I looked at number of results I can retrieve. I look at hybrid versus hybrid ranker versus vectors, right? So these are just all different things that I tweak. And then I run the evaluation, and I run the evaluation on a bunch of ground truth Q&A pairs, usually like 200 is what I run it on. And so then I can see like, okay, groundedness, these are, my average number for groundedness. This is how many got a 4 or 5. This is how long the answers were. This is how long they took. This is whether their citations match the citation in the ground truth answer. And so I can just look at all these numbers across runs and then make a decision of, was that change an overall better change, or was it worse overall? So it's really important when you evaluate that you do want to evaluate on a lot of question and answer pairs, not just on a single one, because what you'll see is that some parameters might be better for a single QA pair, but then won't be better across 200 pairs. So really want to run across as many as possible. So that's evaluation. 1 minute left. So example uses, we've seen thousands and thousands of developers deploying RAG apps with Azure AI Search. Many of them using that a repo that we shared earlier. It's a very, very popular repo, but you can also develop your own approaches. But people are using it for public government data, for internal data, company meetings, for sales data, sales manuals, product manuals, technical documentation. So many different use cases in order to make document search more accessible, right? So we're trying to make it easier for people to be able to get their answers from some knowledge base, right? And that's the real power of this combination of great search plus great LLMs. For next steps, you can learn more about AI search. You can read that blog post. You can start to deploying that RAG chat repo that we shared. And you can also check out AI Studio, which has a bunch of RAG options as well. And if you have any additional questions, we are going to put a GitHub discussion thread link in the chat. And so you can go to that discussion thread link and start posting any follow-up questions in the chat that we didn't get to. You all had a lot of amazing questions in the chat and great comments as well. But if you have any more questions, we're happy to keep answering them in the chat. We hope that you submit to RAGHAT. There is a prize specific for AI search, best in Azure AI Search. So looking forward to seeing what you make with that. All right, Farzad, any last words? We can go overtime, they said.
Cool. No, I hope everyone has a great time hacking away. I think this is such a cool, fun time to be exploring with generative AI and RAG and Azure AI Search. Highly recommend using it. It's so cool to play around with, and I'd love to see what everyone builds.
Sweet. All right. Go ahead and put those follow-up questions in the chat, and we'll see you there. Bye, everyone.
All right. Thank you, Farzad. Thank you, Pamela, for an excellent session. As we've been saying and putting on the screen, we really appreciate your feedback. So if you could take a moment and let us know what you think, if you have any suggestions or want to rave about the excellent session. The event code for this is 2330. Thanks and have a great day.
Hey, everyone. Hope you enjoyed today's session.
If you aren't registered yet for RAGHAC, you can register now at aka.ms/raghack/register, and you can introduce yourself on our forum. You can start hacking either by looking at one of our code samples or just starting from scratch. If you have any questions along the way, feel free to post them in our GitHub discussion forum, and you can also attend live office hours in our Discord. Once your project is ready, make sure to submit it before September 16th at 11:59 p.m. PT to be eligible for our cash prizes. And of course, make sure to join our upcoming live streams to learn more about RAG. Thanks for joining.